When we do a hypothesis test, setting up our null and alternative hypothesis is step one. That's how we set up the test. And from there, we need to actually know which one of these cases is the one that we should trust. And in order to do that, we're going to use what's called a test value. I won't go quite into what the test value is now. We'll do it in a later video, but now just know that it's a thing that we are going to obtain later. In general, there are 3 different types of hypothesis tests we can perform, mainly because there are 3 different options for our alternative test. So we'll start with a right-tailed test. We use a right-tailed test whenever we have a greater than in our alternative hypothesis. When I draw my normal distribution, it's going to look like this picture here. We have the right tail shaded. And essentially what we're going to do is see if our test value, once we know how to calculate it, is in my non-shaded region or my shaded region. And that's going to tell me which one I should accept. My white region, my non-shaded region, is called the non-rejection region, and my red region or the shaded region is called the rejection region. And I'll talk about exactly what we are rejecting here in just a second. But essentially, this is what we want to know. Is our test value in the non-rejection or the rejection region? We have something similar for what's called a left-tailed test, when our alternative hypothesis has a less than and we're shading the left-hand tail. And we have the same thing. If it's in the white region, it's the non-rejection region. And if it's in the shaded region or the red region, we're going to reject. And once again, we'll talk about exactly what we're rejecting here in a minute. The third case is the not equal to case, and this is where we shade both tails. It's also known as a two-tailed test. So we have 2 rejection regions, and just the center is the non-rejection region. So what exactly are those regions, and what is it we're rejecting? The rejection region means we reject H0. It says H0 is false. We are going to say that our null hypothesis is false if our test value falls within the rejection region. Our non-rejection region says that our null hypothesis is probably true. We can't say it's definitively true. Really, what we say with non-rejection is there's not enough evidence to say that it's false. And that's how this is always worded. So we never say our null hypothesis is necessarily true. Instead, we say that there's not enough evidence to tell us that it's false. So we now know what the rejection and non-rejection region mean, and we know what the pictures look like, and we know that we're trying to figure out whether our test value is in the rejection or non-rejection region. So the question is, how do we figure that out? And that's known as the critical value. The critical value is these bounds. It separates our non-rejection and our rejection region. And so now the question is, how do we find the critical values? Our critical values come from something called the level of significance, which we denote by alpha. And this is given to us in any particular problem. It's how accurate do we want to be? In particular, what's our percentage of time that we say that our null hypothesis is false when it's actually true? Here I have a right-tailed test drawn, and essentially alpha corresponds to this area, this shaded area here. And so the critical value is the z-value that corresponds to alpha being in the shaded region. Let's look at a couple of examples of finding these appropriate critical values. So let's suppose we have a left-tailed test and alpha is 0.1. This means that the left-hand side of our normal curve is shaded, and the shaded area represents 0.10. And in order to find the appropriate z-value, we need to result to the normal table. Here is our normal table, and remember the area are the numbers in the center. So we essentially need to look through this table and find as close as we can to 0.10 in the center of the table. And we're going to find that over here at 0.10. 1003. If I go to the left, that corresponds to negative 1.2, and up corresponds to 8. This tells us that our critical value, this value here, is negative 1.28. The next one, we have a right-tailed test, and we know alpha is 0.025. This tells us that we have the area shaded to the right, and that shaded area corresponds to 0.025. Because our z-table always gives us the area to the left, we need to find the area of the non-shaded region, which is 1 minus 0.025, or 0.975. So we need to find 0.975 in the center of the z-table. Looking at our z-table, we now need the second page, and we need to find 0.925 in the center, or at least as close as we can get. And we can get 0.9251, which is really close. This corresponds to 1.44. So our critical value in this case, 1.44. As our last example, we want to find the critical values for a two-tailed test with alpha equal to 0.02. So the shaded area has area of 0.02. However, it's broken up into two pieces. Because we know the normal distribution is symmetric, I can say that each one of these is 0.01. And then that respects my symmetry and gives me a total shaded area of 0.02. Going back to my normal table and finding 0.01 in the center of the table, the closest I can get is 0.0099, and that's negative 2.33. That tells me that the critical value on the left is negative 2.33. And because of symmetry, I can now say that the critical value on the right is positive 2.33. Anytime we have these two-tailed tests, my two critical values will be only different by a sign. One will be positive and one will be negative.